Hey Science9, welcome to your first lesson on space exploration. Today we're going to get through quite a bit of stuff in this unit. We're going to start out by talking about astronomy versus astrology and what the difference is. Then we're going to get into how to find things in the night sky, so how we actually track that. And after that, we'll talk about some ancient theories around astronomy and what's happening in the night sky. And finally, we're going to compare geocentric and heliocentric views, heliocentric being the correct view in our current understanding and correct understanding of our solar system. So let's get into it. Right away here, we are going to talk about astrology versus astronomy and the key difference between these two terms. So astrology is known as the study of the traditions and beliefs that people have about celestial bodies, not to be confused with the science of astronomy. And astronomy has to do instead with the scientific study of celestial objects such as stars, planets, comets, and galaxies, and phenomena that originate outside the Earth's atmosphere. So astrology, you kind of know from astrology charts and knowing what your astrology sign is and all that kind of stuff. That is not a science. It is not related to astronomy, which is instead having to do with, the science of understanding the universe around us and things that are outside of Earth's atmosphere. So in this lesson, of course, we're going to be focusing on the science in science class. So we're going to be talking about astronomy, but we're also going to dive a little bit into kind of past astrology or understandings of, the universe around us and what people used to think. So what is a celestial body? At the end of the day, what's the definition? Well, a celestial body is anything that we can see in the sky. So the sun, the moon, other planets, stars, all of that stuff, we can say or fall under the umbrella of it being a celestial body. So that's a key definition to know. And that's what we can use as a general term to talk about planets, to talk about stars, to talk about galaxies. We can talk about all of these things as celestial bodies. So to understand a lot of this, we're going to first talk about frame of reference. And this is going to tie into later on our understanding of geocentric points of view. But a frame of reference is a set of axes of any kind that is used to describe positions or motions of things. So we can actually observe kind of the idea of frame of reference really easily. If you look first with your left eye and then with your right eye and kind of go back and forth like that, you can see how things shift just a tiny bit. And I can actually go kind of like this as well. That's called parallax. And it's the idea that as we change our point of view, that's our frame of reference. And frame of reference is incredibly important when it comes to astronomy and physics in general, actually. It's something that we really care about because the way that we motion position or measure position and speed will have to do with our frame of reference. So again, a frame of reference is a set of axes of any kind that is used to describe positions or motions of things. So it's kind of like us saying, okay, we're looking from this set of conditions, this position or this speed, and then we're comparing everything to that position or that speed. So as a quick example, when you think about Earth, it's zooming around the sun, right? We're moving incredibly fast. So our frame of reference when we look at the night sky is of course from Earth. That would be different than our frame of reference if we were on Mars or on the moon. We'd be looking at things in a different way. So it's important to consider our frame of reference when we're looking at position or motion of things. The stars, the sun, and the planets do not rotate around the Earth, as we're going to learn later on when we talk about geocentrism and heliocentrism. But they don't rotate around the Earth, but seem to because the Earth is rotating on its axis, and we're on the Earth. So our frame of reference being on the Earth makes it seem like everything else is moving around us. But that's not the case. It's kind of like when you're in a car and you're beside a really big truck or a bus and it moves forward and you feel like you're moving backwards as a result because that's all you can see. In the same way, we're on this moving Earth. And when we look out at the universe around us, we kind of feel like we're fixed, we're not moving, but everything else is moving. But of course, that is not true. It's all moving. So we all have to consider things as relative to each other. And we're going to talk about that later on. This is such a beautiful picture. It's a time-lapse photograph which shows the movement of stars as Earth is rotating around its axis, which is really neat. So to locate positions on Earth, the equator and the prime meridian, latitude and longitude, are the axes used. So let's get a little bit into how we can actually measure the position of celestial bodies to communicate it to other people. There were many early tools that were invented to study and predict celestial motions. So sailors and other explorers tested these instruments in their travels to uncharted places of the globe. Of course, very useful for knowing what direction they were headed, right? The stars have long been used to figure out direction. And azimuth and altitude are what we're going to talk about. They are ways for us to represent the position of things in the night sky. They are calculated from the observer's position. I don't like calculated. Measured is a better word. Azimuth and altitude are measured from the observer's position and are used to locate objects in the sky. Now, what would be interesting then is if you had a friend who was across the country, let's say they were in Quebec, would they have the same altitude and azimuth as you would from their position? And the answer is no, it would be slightly different because of the difference in where they are located. So azimuth is measured in degrees from due north, and altitude is measured from the horizon. Azimuth is probably the more confusing one, but what we do is we start from north, and then we rotate clockwise until we reach the position. So you have to use a compass for this. You point the compass north, and then you figure out where it is in relation to north in the clockwise direction. Well, altitude is how many degrees above the horizon it is. Okay, so let's get into this a little bit more. Azimuth tells you which compass direction it can be found in the sky. So an azimuth of 0 degrees would be exactly north. If you go 90 degrees clockwise from north, you're going to end up at east. So an azimuth of 90 degrees would be east. If we go 180 degrees, well, then we're south. And if we go 270 degrees, that would put us at west. Okay, and then finally, if we're at the full 360, which we never actually write 360, we could write 359 as just a degree left of north, right? But if we went to 360, that would be north again. So this is again the clockwise angle from north, and we measure this with a compass. So this diagram is great. It shows the sun, and we're trying to figure out the azimuth of the sun. So if this is north, we go 90 degrees to east, and then we have another, let's say 70 degrees to get to the sun. So right now, this would be 160 degrees for the azimuth, or around there. Now, as we go through examples of this, it's all estimations, okay? We could be 5, 10 degrees off. That doesn't matter. It's just an idea. We're not actually measuring this formally, right? We don't have what's called an astrolabe, and that's something that is actually important as a term, and I'll make sure it's in your notes. But an astrolabe is what we use to measure these values, kind of a neat instrument, and they're not even expensive. But yeah, that's how we figure it out. Altitude, on the other hand, tells you how far above the horizon the object is. So if we point straight overhead, that would be 90 degrees. So directly right in the middle of the night sky, that's 90 degrees. A point on the horizon would be assigned 0, and then halfway up the sky would, of course, be 45. So with these two angles together, we can figure out the position of really anything in the night sky or in the sky period. So zenith is kind of a neat term. That is the directly overhead position. That would be the 90 degrees. The highest point in the sky directly overhead is the zenith. Okay, so let's take a look at an example and try to figure it out together. So here we have north at the very top, which makes it nice and easy. We have a star that's kind of in this half sphere, like a dome, okay, type model of the night sky, which makes it useful for us to kind of figure this stuff out, to view that dome. It's a way for us to view this in 3D. So let's try to figure out exactly where we would be when we take a look at this. So first of all, here's our north. We're rotating clockwise. So if we rotate clockwise from north, this is right around 45 degrees, maybe a little bit less, but let's just keep it simple for this. And we're going to write in a different color that shows up, 45 degrees. Let's go with yellow. So I have an azimuth of 45 degrees because I have to rotate 45 degrees from the north position to get to there. Now for altitude, this again, I would say is right around 45 degrees. Straight up is 90. This would be 0, and that's just right about halfway. So I would say that this would be this star at an azimuth of 45 and an altitude of 45 degrees as well. All right, from a specific point, a star can be found using the coordinates below, altitude 32 degrees, azimuth 45 degrees. And Peggy wants to find this star in the night sky. So you're trying to talk to Peggy, tell her where to look. How would you describe it? So to physically locate the star, tell Peggy you must face north, turn some direction, and look something above the horizon. What do you think is the right answer for this? So we know that Peggy would have to turn clockwise, so these are the only two possible answers. Okay, the direction is the azimuth, so I'm looking at clockwise 45 degrees, which actually right now puts us on row A already. And then altitude is 32 degrees above the horizon. So the answer would be A. That's where Peggy has to look. Good job, Peggy. You found it. All right, let's take a look at this picture. This is actually directly from a provincial achievement test. What is this student in the picture most likely trying to determine? What are they trying to find? And the answer is they're trying to find the altitude, okay? Because you can see here that they are trying to figure out how far above the horizon this thing is. And I'm assuming this is a classroom because stars don't have a string, but oh well. So that would be altitude for that one there. Okay, here's the really big question that we're going to try to tackle. We're going to try to figure out, and I know this diagram is kind of not great, but we're going to try to figure out the position of star A, star B, which is right here, it's ugly, star C, and star D. And north, cut off for some reason, is right here. Here's east, south, and west. Okay, so if I was looking at star A and I was trying to figure out my altitude, we're doing altitude first. So zenith right here, right, that would be 90 degrees. I would say that this is about 15, 20 degrees from the zenith. So I'm going to go ahead with 70 degrees. I'm going to keep it simple. 70 degrees for that. Now we have the altitude or the azimuth to figure out. So here's north. 90 degrees takes us to east. Another 90, so we're at 180, takes us to south. And then when I take a look at this, I think it is closer to west than it is to south. I would maybe peg this at 55 degrees here. Well, I have another 35 degrees left over here. I don't know if you guys jive with that, but that's where I'd put it. So if I add 90, 180, and then 55. That's going to put me at 235 degrees for the azimuth. Okay, for B, I have here an altitude. I'd say that's pretty close to 45 degrees in that position. It's about halfway up the dome towards the zenith. So let's just go with 45 degrees for that altitude. Azimuth now, here's north. So I go north to east is 90 degrees. And then I'm going to go another, I would say that's almost smack dab on 45. I'd say that's about halfway between east and south. So let's go with 135 degrees. And all I've done there is 90 plus 45 gives me 135. All right, let's take a look at object C. When I take a look at this, I'd say that that is quite low in the night sky. Maybe we put that somewhere at 30 degrees-ish, 25, 30, somewhere in that range. Let's keep it simple and go with 30 degrees. So if I've got 30 degrees here for the altitude, and then for my azimuth, once again, I'd say that's about smack dab in the middle, and I'd put that at 45 degrees, because I just have to rotate 45 degrees clockwise from north. So again, it's important for us to know what clockwise is versus counterclockwise for us to do this. And finally, I've got D. That is way up in that night sky. I'd say that that's almost close to the zenith. Let's put it at, I don't know, 10 degrees away from the zenith. So let's go with 80 degrees for our altitude. My azimuth, I'm going to actually just kind of consider that all the way from north around would be 360. And this is not quite, I'd say this is less than halfway. I'd put this maybe at something like 35 degrees again. So if I have 360 degrees minus my 35 degrees, that's going to put me at 325 degrees. So I'm going to go with an azimuth of 325 here for D. All right, hopefully that made sense. That's kind of how altitude and azimuth works. And you will see questions on your unit test for this, where you're going to find the altitude and azimuth for different celestial objects, but we're also going to get some more practice on it as well. Okay, so let's talk a little bit about our understanding and how it's changed of the universe and solar system and celestial bodies in the night sky. So ancient cultures tried to explain the motions of stars and planets with their frame of reference being the Earth, and they explained it in different ways, and we can find value in these explanations. Now we have a better scientific understanding, but that doesn't mean that these understandings aren't neat to learn about. By the way, for this, you don't have to know the specific understandings. You just have to know that our understanding of the universe has changed over time as our instruments have gotten better, as our scientific method has gotten better, that sort of thing. So first of all, the Big Bear, part of Ursa Major, I'm going to butcher this, and I'm sorry, Algonquin, Iroquois, and Narragansett, believed the constellation was a bear running from hunters. Snohomish First Nations believed the Big Dipper's 7 stars were 4 elk running from 3 hunters, which is kind of neat. The Lakota tribe of North America, the Platus cluster, I might be saying that wrong, a lot of words here that I am not used to pronouncing. 7 women who are giving birth, which is kind of neat because these are like star nurseries. But yeah, the constellation is known as I can't say that. Samamik, I don't know, which is apparently an archaic plural of the noun kamam, which is women. The First Nations people of the Pacific Northwest thought the night sky was a pattern on a great blanket overhead. The blanket they believed was held up by a spinning world pole, the bottom of which rested on the chest of a woman underground named Stone Ribs. So all neat ideas in terms of kind of how the universe operated and was to be. So, objects in the night sky have fascinated humans throughout time. The explanation of how these celestial bodies came to be are even more fascinating. And as we learn kind of the science of it and how it works, right, it's a different explanation that's really neat and rich. Ancients developed their ideas of what was happening in the sky and explained it with their frame of reference. And the constellations, which you probably know about the constellations, were patterns that they believed told stories about people. And this is a big part, of course, of astrology. So what is a constellation? Well, a constellation is a group of stars that form a picture or figure in the night sky. Officially, there are only 88 constellations. So for example, Orion, and you can look it up and learn more about it. And hey, this is a great time to look into the night sky as well and see some of these things. Well, an asterism is an unofficial recognized star grouping. So for example, the Big Dipper is not a constellation. It is instead an asterism, which just means that it's not officially understood as a constellation. So 2 terms that are important to know. Stars are not always in the sky at the same time, but change position over time, giving rise to the creation of calendars. The sun and the moon have their own patterns of rising and setting. The moon also has phases. Mercury, Venus, Mars, Jupiter, and Saturn were special stars, was the previous understanding, called planets, meaning wanderer. And stars rise and set earlier one day to the next by 4 minutes, not including the planets, right? We're talking about actual stars here. This means that each month would have a new set of stars in the sky, and people noticed this and created calendars based on the fact that the night sky was changing. One example of, again, ancient understanding and, looking at the night sky is Stonehenge. Was constructed in early stages between 3000 BCE and 1100 BCE. Stones were set that they could calculate day length and the amount of sun per day, which is, of course, really important for things like farming. So it helped farmers to figure out when to plant their crops and when to harvest their crops. And also some stones indicated special days of the year. So based on where the shadows ended up and what could be viewed through gaps between the stones, that sort of thing, they could actually figure out then what was happening, when it was a good time to plant crops, etc. So the ancient Celts set up megaliths in concentric circles at Stonehenge to mark the winter and summer solstices. We're going to learn about that in just a second. So to track the actual motion of each celestial body in space, you need to use the stars as your frame of reference instead of the Earth. And the reason why is the Earth is constantly moving, right? It's the same way as when you look at something far away, it stays in your field of view for longer than if you're looking at something close up while you're driving past. So if we look at stars which are incredibly far away and compare other stuff to those stars, then we have a better understanding of how things are moving than if we compare it to its motion relative to Earth. So to do this, you would make an observation of which celestial body you are studying and include other stars in relation to it, make subsequent observations and include those same stars. Over a period of time, you would be able to determine which direction the celestial body you are studying is actually moving in relation to these very, very, very far away stars. And that gives us a better understanding of the movement of celestial objects. Okay, some more terminology here. Solstice, a day when the Earth is positioned so that it gets the most or the least sunlight compared to other days of the year. So we have the winter solstice, which is the shortest period of daylight. That happens on December 21st. And then we have the summer solstice, which is the longest period of daylight, happening on June 21st. So in the Northern Hemisphere, those are 2 days that are very important. And that is, again, the shortest and the longest day in terms of daylight of the year. So solstice, longest and shorter days. Then we have the equinox, equa being like equal. It represents the time when day and night are essentially the same in length. So if we take a look at this, March 21st and September 21st, vernal and autumnal equinox are kind of 2 days when we have day and night taking up the same amount of time. Chichen Itza in Mexico, the Mayans of Central America built an enormous cylinder-shaped tower to celebrate the two equinoxes. I haven't been to Chichen Itza, but I did go to Tulum, and it was really neat to see some of the stuff there. So let's talk quickly about geocentric and heliocentric versions of our solar system. So first of all, the geocentric model, and you learned all about this in the Cosmos video. Since the sun, moon, and the stars seem to rotate around the Earth, people believe that Earth was the center of the universe, which of course is not true. So it was first proposed by Aristotle and Ptolemy. It was the main theory for celestial motions for almost 2,000 years. Ptolemy gave planets another level of circular motion called epicycles to account for the non-circular orbits around Earth. So what would happen is sometimes planets would seem to actually go a little bit backwards in the night sky, and they couldn't figure out why that was. Of course, it had to do with Earth's orbit and how things changed from our frame of reference because the Earth was moving. So how they explained that retrograde motion of sometimes the planet moving back is they said, well, the planets must also be going in circles or orbits around the orbit of the Earth. And, very confusing, but that was the idea. So it resulted in this kind of pattern as it moved. But again, wrong. But it's how they explain that backwards motion that wasn't expected to occur. So here we have the Earth in the center, right? And then instead, here's the heliocentric view of the sun in the center, which of course is correct. But what this is missing, because they're still showing orbits on orbits, is the fact that they actually move in an elliptical orbit instead of a circular orbit. So Johannes Kepler, a German mathematician, calculated the movement of the planets and found that they moved in an ellipse, oval, rather than a circular orbit. And this explains basically how things were moving and got rid of the orbits on orbits that were still kind of happening on solar system models. So it explained the movement of the sun, the moon, and the other planets through the sky. And here we have some pictures of elliptical orbits, right, of different things in our solar system going around the sun, which is the center. This was further explained as Newton proposed the universal or the law of universal gravitation, so explaining how gravity worked and finding a law that could actually calculate gravity. And this provided an explanation of why things moved in an elliptical orbit and the idea of gravity from the sun, pulling everything towards it. And as a result, there are points where planets are moving faster in their orbit, and then points when they get to the furthest part of their orbit where they're slowing down and then coming back towards the sun. And this was the end of kind of finding out and understanding of how things are moving in our solar system. So in summary, geocentrism, wrong. Heliocentrism, right. And things are moving around the sun. The solar system's planets are moving around the sun in elliptical orbits. All right, that's it for today. We'll leave it there. Have a good rest of your day.